purpose of this video is to talk about how we can write the code to implement a JAGS program. And we're going to begin by loading and installing some programs. This is the key one, runjags. These guys have nothing to do with JAGS, but I just put them in anyways because I use them to manipulate and visualize data. Coda is something that's discussed in your notes, but isn't that high of a priority. And these are two things that I put in because it's my understanding that they actually will help, although I'm not exactly sure why. So the first thing we're going to have to do is get the data. So recall, we're doing a study where we're trying to determine theta, which is the Bernoulli binomial parameter that's associated, in this case, trying to determine that value for handedness, the proportion of people that are right-handed. So here we have the data in an Excel spreadsheet. We've polled 10 individuals and found that 9 were right-handed and 1 was a lefty. So we need to begin by bringing this data in, making it available. So we're going to create a data frame called df. This is all the code that does it. And available on eClass should be this Excel spreadsheet, handedness SV. So that's being imported and made into a data frame called df. This thing is not essential, but it's something that I like to do just because it'll show me what my value of df actually is. And implementing that produces this as output. And you can see that df is a data frame that consists of 10 observations and a single variable. And this is the really important part. This is actually the guts of it. This is the model statement. And the model statement is really important. We're going to begin by naming it. I'm going to name this thing model. My model, I should say. And any sort of valid name will work. I mean, you could call this cat or dog or mouse or anything. That's going to be followed by this bit here, which is put in exactly like that. Quotation marks, the keyword model, and an open parenthesis. And at the very bottom, going to have to match the closing parenthesis and the quotation marks. And then what we have here, priors and likelihoods. Notice the fact that these have the pound sign, which means that they're going to be commented out. They're not going to be executed, but they identify that this is the prior and this is the likelihood. So if we go back to Bayes' theorem, probability of theta given data, and now I'm just going to jump directly to the proportional so I can ignore the marginal probability of the data. It's proportional to the probability of the data given theta times the probability of theta. So there's our prior. Our prior is a beta distribution with parameters 14.5 and 5.5. That is our prior. And here we have our likelihood. And our likelihood assumes that each one of those values of y is going to arise from a population that is Bernoulli distributed with parameter theta. And that's really our target, theta. And this whole thing here represents our likelihood function. And you can see those things in this flowchart as well. Here we have the likelihood function. The values of y are assumed to arise from a Bernoulli distribution with parameter theta, which is our target. And here we specify the prior as being a beta distribution with these parameters. So what's going on with some of the detail here? For 1 in knobs, open parenthesis, and then this open parenthesis and its closed parenthesis, what's that all about? Well, if we come back here and look at our data, there's our 10 individuals. And as I said earlier, although it's not explicitly stated, each one of these has a position we can think of as I. So this is position 1, position 2, position 3, all the way out to position 10. And so what this loop is, it's going to loop over all 10 values. So the value of knobs is 10, which isn't really obvious now, but we'll see that in a moment. So it's going to loop through all these 10 different values, right versus left for those 10 individuals, and it's going to assume that each one of those ones and zeros arose from a Bernoulli distribution with some sort of parameter theta. So that's our model statement. Now we have to do some more preparatory work with the data. So remember, we've got this data frame df that we created here. And then this can be any keyword. This could be cat or dog. But this, excuse me, that could be any word, any valid object name. This is a keyword. Type it in exactly like that. It operates on df and creates this thing called data file. Now up here, we had this knobs. Where did knobs come from? Knobs came from this line here that created this new variable knobs, which is going to be equal to the length of what previously was df. And since df has a length of 10, what's going to happen is the value of the variable knobs is going to be equal to 10. Now, we actually could have specified 10 in here instead of using knobs, but typically we tend to use words instead of numbers. It makes it more easy to modify our file if we have to. So now what we've got is this new object called data file, and although not required, it's always good to have a look at this. And so I've done the structure of data file, and there we can see the structure, and it looks nice and neat and clean, and we can see that it's got two variables, the y, which is a series of ones and zeros, and knobs, which is this value of 10, which is what's going to go up here. Then the last bit we're going to do is, again, this is any valid object name. This is a keyword, so you have to do it exactly like this. And data file here corresponds to this name here. So essentially what we're doing is taking this data file that we created, operating on it with this function, and putting it into a format that JAGs can understand. Initialization. Remember when we did give sampling, we had these three parameters, theta 1, theta 2, and theta 3, and we initialized them. Now, in this particular case, we don't have three parameters. We've only got one parameter, theta, that we're interested in, but we're going to want to make three chains. We're going to want to make three chains. So here I've created three different initialized values of theta, and I've specified them like this, added a little bit of variability. List is a keyword. Theta here corresponds to theta here. Then what I'm going to do is create another object called results. And again, this could be any valid name. Cat, dog, mouse. Runjags is a keyword. Type it in exactly like that. Open parenthesis. And there's the closed parenthesis down there. Whole bunch of lines separated by commas. Model is again a keyword. My model, where does that come from? My model comes from way up here. There's my model that was created. So the name of the model, again a keyword, is my model. What are we going to monitor? We're going to monitor theta. Theta is what we're interested in. The Bernoulli binomial parameter, the proportion of individuals that are right-handed. Data. We have to specify the data, and the data is called data for JAGs. Where did that come from? That came from right here. So we had our data file. We used dump format to put it in a form that R would recognize, and that was called data for JAGs, so we specify that here. Here we've got inits, and we need this keyword list, and what we do is specify the 3 different values of initialized thetas, inits 1, inits 2, inits 3, inits 1, inits 2, inits 3. We want 3 chains. We want 3 chains. This implies 3 chains. Method is parallel. Apparently, with runjags, it can do this thing in parallel, so I'm specifying that. Adaptation. Remember when we talked about give sampling and this whole idea, particularly with the Metropolis algorithm, that we had sigma is equal to 0.02, sigma equals 0.2, sigma equals 2.0, and what we discovered was, depending on the value of sigma, that had a big effect on the effective sample size. So essentially what happens is we specify this adaptation period, and then what the program does is it just messes around and tries to determine what the optimum value would be of something like sigma if it's needed. The idea of burn-in, let's say we've got a large number of iterations as shown here. Initially it starts, quite a ways away, but eventually it tends to settle down and something like that. And so essentially these first observations, we want to toss those away because obviously we don't want to include this stuff here that is really quite a ways away from the equilibrium around which it's ultimately going to settle. Autocorrelation. Okay, by now we should know what autocorrelation is, and I've specified a lag here of 2, and we call that autocorrelation lags are really important. Once we've done the adaptation with 1,000 iterations and the burn-in with 1,000, then we actually want to sample 10,000. Debugging JAGs is really nasty. This may help a bit. Now notice I've got the pound sign here, so this thing is commented out. It's not going to execute, but if you get rid of the pound sign, you can run failed JAGs, and that may help you a bit if your program should crash. So we've got results. So we call this thing results. So we got this results thing. We use the keyword summary to create a summary of results. And then what we can do is we can create an object called out. That's the consequence of this action. We can just print that. And then the last thing we can do plot results. And that'll make a very nice plot of these results that were developed here.